Hi everyone. So we're going to be talking to Hugo Laurençon, who is a Meta AI, who was previously at Hugging Face, who's going to be talking to us all about vision language models. As usual, he'll be giving out his talk first for about 40 minutes, then we'll have a 20-minute QA. QA is going to be facilitated by Peter Tong, who's at NYU. And today I'm committee of the machine learning meetup. So hi to George, and over to you, Hugo. Looking forward to it.
Okay, thanks for the introduction. Let me share my screen. Do you see it full screen now?
Yep, looking good.
Okay, perfect. Yeah, so in this presentation, I will talk a bit about how to build foundation vision language models, the research questions in this field, how we built in practice our Idefics2 model, and the challenges we faced. I will talk about architecture, data, and a bit everything. And maybe if we have time in the end, I can talk a bit about our latest model, Idefics3. So first of all, what is a vision language model? So we will say that it's simply a model that takes as input text and images, and that outputs text. It can output more than that, more modalities than that, but for this presentation, we will focus only on models that output text. So the most famous ones are ChatGPT, so GPT-4v, GPT-4o, Gemini, and also Claude 3. So with vision language models, you already have a lot of first challenging tasks. So here you have a few of them on the slide. So for example, you could have a letter and try to extract an information in this letter automatically. So here the contact person name, or you can have a figure where you first need to read the information, read the text in this figure, understand the different curves and the different numbers, and compute the final answer for a certain question. You could also solve scan math exercises or equations just with a picture, or comparing, finding the differences between several images. So it was already some good first use cases, but maybe not the ones that we will use a lot in the end in the industry. Maybe we can discuss quickly about the real-world scenarios for the applications of the vision language models and where they can be extensively used in the industry. So, for example, so one example is on web design. So essentially, you prompt a vision language model with a screenshot of a certain website, and you ask it to produce the code to recreate this website. So it can be super useful to directly iterate super fast from ideas to production. Or you can solve yeah, scan math or physics exercises that require not only to understand the text, but also understand the different figures. Or you can automate a lot of different tasks that were done previously by humans and that were very repetitive. So, for example, extracting information accurately in a CV. So in this presentation, we are interested in making a foundation multimodal model. So we will focus on different things. First, on the vision and text modalities only. We want a model that is good at a lot of different tasks, and not a model that is only specialized at one specific task. And besides just the performance, we would like our model to be efficient at inference. And this is super important for applications like robotics, where you need to consistently prompt your model with a new image, and you need to have quick outputs to do fast iteration. And finally, we want to leverage pre-trained backbones, so pre-trained language model and a pre-trained vision encoder for an efficient training. So we will not train our whole multimodal model from scratch for efficiency reasons. So at that time, when we did this study and when we released the paper, the previous VLMs had common issues. So first of all, they lacked a long pre-training stage. They were trained only on a few million images, and maybe that they could be under-trained. Second, they were very inefficient at inference, having a lot of or too many tokens per image. And so that's the point that I mentioned just before, for example, for applications for robotics, where it can be a problem. Also, before, they were simply unable to take an arbitrary number of images as input. And eventually, from a research point of view, it was problematic because you had a lot of unjustified choices in the papers. They were simply um, showing their new architecture or their training data, but without really showing the ablation results. So we didn't really know where the boost of performance was coming from. So we wanted to address these issues a bit in this study. So the presentation outline is the following. First, we will explore the design space of vision language models. We will focus on the different types of architecture that exist, and also the impact of the pre-trained backbones. We will then focus on making a model more efficient at inference, and also the strategies to be able to trade compute for performance at inference. And also, of course, the training data that plays a very important role. And eventually, we will build in practice, see how we build in practice our model Idefics2 with the training strategies and the training data that we use during the pre-training and during the instruction fine-tuning. So for the different architecture, there is one architecture that was very famous because of the paper Flamingo, is this cross-attention architecture. So essentially, you start from a vision encoder that you keep frozen and a language model that you keep frozen, and you are trying to inject the output of the vision encoder to the language model. And the way you do it is via cross-attention blocks. So here in this figure, you can see that every layer within every layer of the LLM, you inject a block of cross-attention. So essentially, yeah, the output of the vision encoder is sent within every layer of the language model via cross-attention. So this is a complex architecture with a lot of newly initialized parameters. So all the cross-attention parameters are newly initialized. So you end up with a model that is much bigger than the original size of your pre-trained LLM. So it's a complex architecture that can be difficult to train, but Flamingo was based on this, and it was very much state of the art at that time. So that's why it was very famous. And more recently, there was the Llama 3.2 model that also used this architecture. So this is not the architecture we chose eventually. We will discuss more about the ablations later. But the other type of architecture that exists, yeah, we can call it fully autoregressive or self-attention architecture. It's an architecture that is much simpler. So the idea is still to connect the output of the vision encoder to the language model. where you can keep essentially the vision encoder and the language model frozen as a first approximation. And the way you can connect them is simply through a modality projection and a pooling. So what is a modality projection? So simply as output of the vision encoder, you have a series of vectors of a certain dimension, and you want to match the dimension of the output of the vision encoder to the dimension of the input of the language model. So you need at least one linear layer for that. So this is what we call a modality projection. And secondly, there is also potentially a pooling that you could do. It's not mandatory, but usually it's done for efficiency. So as output of the vision encoder, you usually end up with a lot of tokens per image. And maybe it's not super efficient, or maybe it's not useful for all the tasks. We will discuss that later in the presentation. So the idea of the pooling is simply to reduce this number of visual tokens to something more convenient for the efficiency at inference and also during the training. So the first thing we did was to compare these two architectures. So we did this on several on different setups. So first of all, we reported the scores during the pre-training as the average score with a 4 shots on VQA V2, text VQA, OK VQA, and COCO. So these are standards benchmarks for vision language models. And we essentially compared the performance of these two architectures while keeping the backbones, so the language model and the vision encoder, either frozen during the training or trained with additional parameters, like for example, with a LoRa approach. So before explaining a bit the difference between the two, I just want to mention that we tried to unfreeze completely the language model and the vision encoder. However, we couldn't get a training that was stable enough. So we tried many different things like reducing a lot the learning rate or doing it in many different stages, but we just couldn't make it work. And in the end, using LoRa parameters helped us to gain expressivity while keeping the stability. So that's what we use. Instead of unfreezing everything, we use a LoRa approach, even during the pre-training. And what we can see is that the fully autoregressive architecture performs worse than the cross-attention architecture when the backbones are frozen. So on this, you have to keep in mind that the cross-attention has much more trainable parameters, so that can be expected in a certain way. However, if you train the backbones with LoRa, it's the other way around. So with the fully autoregressive architecture, first you have an architecture that is conceptually simpler and maybe easier to train. And also you have less trainable parameters, fewer trainable parameters, and fewer total parameters, and a better performance. So this is definitely the architecture we chose in the end. After that, we wanted to check the impact of the pre-trained backbones. So essentially the language model and the vision encoder. So we saw that there was a big boost in performance when swapping, for example, Llama 1 to Mistral 7B, even if they were like of the same size. And it was the same thing with the vision encoder backbones. For example, EvaClip performed better than Clip, and CGlip, which was much smaller in size than EvaClip perform even a bit better. So the conclusion is that the impact of these pre-trained backbones is super important. And then if you don't have good enough backbones, you will have a bottleneck later in your training. And yeah, potentially the resolution of the pre-trained vision encoder can be also important. So now talking a bit about the efficiency at inference. So as mentioned a bit before, you will have as output to the vision encoder, you will have a certain number of visual tokens. And the problem is that this number, if you don't reduce it, if you don't apply any pooling strategy, it can be pretty high. And then it can be inefficient during the training and also at inference. So you would like to find a certain type of pooling that can reduce this number of visual tokens. So we tried very simple approaches like an average pooling or mean pooling, but that didn't work quite well. And in the end, what we use is a perceiver resampler. So a perceiver resampler is essentially a learned pooling strategy where you add, like let's say 400 million parameters to your network. So that's quite big, but it allows you to do an efficient pooling and to reduce significantly the number of visual tokens. So what we showed is that you can still achieve good performance by having only 64 visual tokens per image. And this is important to remember, but we didn't notice it at first, but it's important to remember that the visual tokens, the number of visual tokens is super important for OCR tasks, but is not so important for the other tasks. So if you want to be super good at document understanding, then you might want to increase a bit the number of visual tokens, but for the other task is not critical. So then if you have a very specific use case, you could build your vision language models so that it's very aligned with the number of visual tokens is very aligned with this. A second way to improve the efficiency at inference is to keep the aspect ratio of the images. So what we did is that we simply passed the patches of the images to the vision encoder without resizing an image to a fixed size square images like it was done before. And this way, like because if you only resize to fixed square images, then you need to select your resolution that will be shared for all the images. If this resolution is too low, then you will be bad at a lot of different tasks. For example, document understanding, because this requires a high resolution for the images. But if this resolution is too high, then you will have a lot of constraints because, for example, for an image that is of low resolution, you will need to upscale it to a higher resolution before passing it to your model. And this is inefficient because you don't even need this image to be of high resolution. So this is why we kept the aspect ratio of the image and try to preserve the original resolution if possible. And we showed that it only slightly degraded the performance while allowing a boost for efficiency at inference and during the training. So then there is this question about how many tokens you need to encode an image. So with the current vision encoder, the thing is that first you pass an image through the vision encoder, and then this is fixed, and then you will use this series of embeddings to encode all the knowledge about the image. but maybe you will not need the same number of visual tokens depending on the images. For example, an image of a dog and an image of a page. So here, if I ask you to have a certain representation of this dog, it's pretty easy. But if I ask you to remember everything about this book, you will need a lot of time to remember everything. And then when you ask a question about it, it's much harder. So the thing, um, is that maybe you don't need the same number of visual tokens for all tasks. Maybe for some tasks, you need a very few number of tokens. It's fine with it, and it will be more efficient at inference. And maybe for others, for example, document understanding task, you will need a lot of tokens. So this is why we try to show with the image splitting strategy. So this image splitting strategy was, for example, introduced in several papers like uReader or Sphinx. So the idea is you have an original image that is of high resolution, and then you will split the image into several sub-images and encode each of these sub-images separately. So this way you can artificially increase the number of tokens, increase the number of visual tokens for your image overall, because you will have the visual tokens for all the sub-images stacked together. Then to learn also the overall representation of the image, you can take the original image, downscale it to a lower resolution image and encode it as well, and stack it with the other visual tokens. So this way, for example, let's say we have 64 tokens after our perceiver resampler. Let's say we have 64 tokens to encode each image. Imagine if we decide to apply this image splitting strategy by always splitting an image into 4 sub-images plus adding the original image with a lower resolution, then you end up with 320 tokens. And then we wanted to see if having 320 tokens instead of 64 was beneficial for certain tasks. So this is what we did. We did this image splitting strategy by training, during the training, by applying the image splitting strategy or not. So it means that for some images, we didn't split them, and we tried with the regular approach. And for others, we decided to split them. So we had a different style of resolutions during our training. And what we showed is that we didn't really see improvements for most of the tasks, except the task requiring to read text in an image. So, for example, text VQA and doc VQA. Here we can see that for MMMU, MadVista, and MMPatch, it's even a bit better with fewer tokens per image. But for doc VQA, so doc VQA is essentially a task where you have a document and you have a question about this document, like extract certain information, things like this. And here there is a big gap between a model that has only 64 tokens per image and a model that has 320 tokens. So we didn't try at that time. We didn't try even more tokens per image, but of course, if you increase it, you expect to have a even bigger boost for tasks like WQA. But the thing to remember is that it's not important for all use cases to be super good at OCR. So if you don't mind being a bit worse on OCR, then you can be much more efficient at inference. So then I will talk a bit about the training data. So let's start with the pre-training data. So you have different families of data. You have the image text pairs. So here you have an example, two examples found in the web. The way these image text pairs are data sets are usually created is by crawling the web. So you find all the images, and in the HTML code, you are looking for the alt text that is written by developers. The problem is that these alt text are often, so first of all, missing, and when they are here, they are short, non-grammatical. However, the good thing is that there is a strong alignment between an image and a description. And on the other side, you have the multimodal documents. So here you can simply imagine any website that you uh, that you can have in mind. So for example, a news website where you have a succession of one image, a text, one image, a text, and so on. So this is what we call interleaved image text documents. And here you have a longer and higher quality text, but the thing is that you have a weak alignment with the text not necessarily describing exactly the picture, but you will still have the context that is shared. So maybe this is useful for the pre-training. Um, so in our previous paper, Obelix, this is what we did, trying to create this interleaved image text data set, and also open source the data set. So we did a complex pipeline starting from the command crawl data to eventually obtain a data set of 140 million documents and 350 million images. And we took a lot of time filtering the data, deduplicating it, and everything. We also tried to compare the quality of the text in our datasets to other text-only datasets, and we saw that we had a very good perplexity, so showing that the text is of good quality. And eventually, oops, I don't have the slides anymore, it seems, but we checked oh no, it's just after. We checked also the performance of different models. Like one model trained on Lions, so image text pairs only. One model trained on Obelix only, so only on interleaved image text documents, and one model trained on both. And we saw that it's the combination of the two that is that performs the best. So if you want the best of, if you want to have the best model, you need to use different types of data. At least this is what we found. Um, and just to go back to the previous slide, so yeah, talking a bit more about the image text pairs. What we did with Idefics2 is that instead of relying on alt text for the image text pairs that are yeah, very short or non-grammatical, we decided to use only synthetic captions. So for that, we used the dataset Lion Coco, comprising 600 million image text pairs that were captioned with the Blip2 model, I think. And we performed the ablation and saw that it improved the scores and allowed a faster training. So yeah, we checked in practice that synthetic captions can reduce the noise of the alt text from the web and allow a faster convergence. We also wanted, even during the pre-training, to add a PDF, scan PDF with associated text. So the reason is that we wanted to have a model that is good at OCR, a model that is good at reading text in an image. So we use the datasets PDFA and IDL that are massive collections of PDF with the associated text. and we simply prompted the model with the image of a document and asked to transcribe the text in it. And it's a very simple objective, but that works super well to make a model learn how to read the text in an image. Another type of data we added was the website dataset that we created. So the website dataset is a dataset of 2 million purely synthetic examples of images of screenshots of websites with the corresponding HTML and CSS code to recreate the website. So the idea is simply to prompt your model, your vision language model with the screenshot of a website, and then you will directly have the code to recreate the website. So this is what we did, and in the end, we could generate pretty like simple website applications, but still that was nice to see that you could even generalize to handwritten websites. So now that we talk about the training data, we can see a bit the details about the training of our model Idefics2. So we use a multi-stage pre-training approach. The reason for this is only because of efficiency and saving resources. So during the stage one, we kept a max resolution size of 384 by 384, and we use yeah, a large batch size. And during the stage two, we increased this resolution. So of course it takes lower, and you also have to reduce the batch size in order to fit in memory. And this is important. This is when we increase the resolution that we also introduce the PDF documents and the image HTML code pairs in the pre-training. Otherwise, it's pretty useless to introduce the objective of text transcription from a super long PDF document if you have a low resolution, because the task is simply unsolvable. I mean, even a human couldn't really read in the document. And in total, we use 1.5 billion images, so that was a lot, and 225 billion text tokens. So we checked the performance of the base model, and we noticed a big boost in performance in the especially in the OCR abilities, so measured with text VQA, for example, compared to Flamingo or MM1, despite having again only 64 tokens per image, and also nice performance on the other benchmarks. So here it's an example of text transcription with the base model, so not even instructed. And you can see that even for a handwritten letter, the model could almost perfectly transcribe the text. And this is an 8B model. So for the instruction fine-tuning, we wanted to create a data set that we wanted to create a new data set because we were not satisfied with the existing ones. The existing ones were mostly distillations from either closed source models or models but that are not necessarily performing super well. So the issue with the previous datasets is that they contained a lot of hallucinations in them. So in a sense, you use training data with hallucinations in your fine tuning. So this is pretty bad. And at the same time, in the literature, there were a lot of small scale, but a lot of different and various and diverse data sets. So the idea is that if you take the time to integrate all of them, put all of them in the same format and just train on this mixture, you have something that is very powerful and that can handle a lot of different tasks. So that's what we did with the Gold Run, where we gathered many data sets on many different tasks, like for example, captioning, OCR, document understanding, table understanding, differences between two images, and so on. And we also open source the datasets. So by training on the Cauldron, we see that we obtain good performance for that time. Yeah, especially on MMMU and MadVista. And we also yeah, train our model. So Idefics2 with 64 tokens per image is the same model as Idefics2 with 320 tokens per image. It's simply that since we train our model with a mix of different resolutions, you can simply choose at inference the resolution you want for your model, for your images. So it's the same model, but just evaluated different ways. And here, what we did is that we had a problem with the Idefics2 is that sometimes the model will generate too robotic answers or too short answers. It's because most of the academic training datasets contain short answers, so the model, when trained on it, was trying to imitate this template. So for that, we used datasets containing a bit more hallucinations, but we still use them just for a few steps, to learn to teach the model how to produce a bit longer sentences. And this is what we did. And in the end, Idefics2 that we call Idefics2 Chatty can, for example, produce long and detailed reasoning about here a question of a table, on a table. And so since we have a bit of time, maybe I can talk a bit about Idefics3. So there are a lot of room for improvements for these vision language models, and also a lot of research questions. So first of all, do we need a pre-trained vision encoder at all? And what's the impact of having one single transformer handling all the modalities? So there are a lot of questions regarding the pooling strategy, regarding the pre-trained vision encoder. Is it needed to have something that is pre-trained, or can we train everything from scratch? Also, yeah, can we do better than the perceiver resampler for the pooling? And also the image splitting strategy is also a nice hack, but something that is pretty ugly. So maybe like can we make something a bit better? So yeah, we essentially in the recent paper we show that there are a lot of room for improvements for many different data sets. So here it's a list of them. The idea is that if you want to be good at something, you simply create a good data set for this specific task. And the thing is that you can do it at scale by creating synthetic datasets. So this is clearly the approach we took by creating our dataset dogmatics. So there wasn't any large-scale document understanding dataset at that time. So what we did, we simply took the dataset PDFA that we described better. We used a text-only LLM to produce question and answers given a certain document. And then in the end, we had QA pairs for each image representing a document. We had a lot of QA pairs on this document. So it was very powerful. And for example, with a model like Laurençon trained on dogmatics, you could almost match the performance of Idefics2, but with a model that is only 700 million parameters. And yeah, with like, to be short, with all of these strategies, we built Idefics3 that is outperforming the Idefics2 8 billion parameters. by being trained on larger synthetic data sets. We also reduce the bottleneck of a too aggressive pooling on DogVQA, for example, where you see a large boost of 13 points. And despite all of that, so you still have a lot of room for improvement because the training was done super quickly on less data than Idefics2 and without waiting for final convergence. It was trained only with LoRa for efficiency, despite the fact that we did not have stability issues. So we could have fully froze the model. And it was also trained only on open data sets at that time. Yeah, so I think this concludes my presentation.
So much, Hugo. Really fascinating presentation. Really, really interesting to me. Great. So I'm gonna hand over to Peter now, who is gonna handle the QA. So Peter, welcome, and I guess you'll hear a few questions coming in from me and George as well. But over to you, Peter.
Well, thank you very much. Thank you, and also thank Hugo for the great presentation. Yeah, so I guess I'll just start with some of the questions from the audience and George. Maybe I guess the first one from George I think is pretty interesting, which is that so what is the intuition for why Perceiver resampler works better for linear projection and how generalizable is a result, and also like is it because of the capacity constraint, or as we are seeing that the community, for example, the recent Q12 or the Pixar model are also moving more and more towards this projection-based method, while the Llama 2, sorry, the Llama 3, still uses the cross entropy or quote unquote flamingo style.
Yeah, so I think so for the question about the perceiver resampler, I think that the reason Qwen2 VL, for example, is not using a perceiver resampler and is using a linear projection is simply to avoid, or I think they are using a linear projection, is simply to avoid the bottleneck you have with a pooling strategy. So now you have a lot of different tasks that require to be good at OCR. And for a frontier model, you need to be super good at OCR. And having a pooling strategy can be hurtful for that. So this is why a linear projection is good, because you have no pooling and you keep all the information from the image. However, if you want to have a pooling strategy, to have something efficient and everything, we found that the perceiver resampler worked the best because we tried very simplistic pooling strategies like mean pooling, average pooling, even transformers encoder based pooling strategies, but that didn't work as well as the perceiver. So I think to conclude, you can say that if you are very interested in OCR abilities and you don't mind paying the cost of it by having slower inferences, then it's just better to do something super simple with a linear projection and without any pooling. But if you focus on efficiency and you don't care that much about OCR abilities, then perceiver resampler was the best option we found.
So thank you for answering. And a question from the audience, from David. He's asking the splitting strategy was you were talking about. It seems to be quite effective. And the question was could during inference time of these model, can the users also manually split the images before sending it to hosted multimodal models like Gemini or other models to get better OCR performance, as you were mentioning this kind of trade-off between the token and the performances.
So the question is about whether a user can do that also for closed source like Gemini.
It's like manually they split it and then send it to the in model.
Yeah, I'm very curious about that. I don't know how, of course, how Gemini was trained, and I think they handle this directly when you like, for example, when you prompt the model with a super large image, maybe they just like split it into several images. However, I really don't know if it works better to do it on your own, because the model will like uh, handle the images as if there were like clearly separate images, and not really sub images from the same one. Yeah, I just don't know if it works better. It's more a hack, I would say.
Yeah, I think. Yeah, and I guess another question from the audience is on the obliques. I know, as you know, you were mentioning like you guys made a lot of efforts on like cleaning and making obliques better, and the question was like, you know, was there any plan, or did you? Because I believe you moved to Meta now. Like, was there any plan to extending it to like multilingual, multilingual, or even other modalities?
Yeah, I think that's a good question, but at least we maybe don't have this objective, but at least we open source the code. So if one wants to create a multilingual version of Obelix, they can. I've also seen several improvements. Well, I don't know if it's improvements, but just extension of Obelix to like a higher scale. So I think it's called Mint 1 trillion.
Yeah.
So it's essentially I think 1 trillion documents. So yeah, it's very much the same thing as Obelix, but with bigger, with more documents. So yeah, the code is online, so anyone can just extend the pipeline to uh, multilinguality or things like this. But we will not, yeah, we will not do it.
If I could ask a question, with the Idefix2, it looks like the doc VQA results are pretty weak, really. Is this because is this purely because there's a lot of high frequency information in documents. You really need high resolution images. You need high resolution information to make the decisions compared to the other benchmarks. Is that the only reason? And why you made a few changes with the latest version, with version 3 of Idefix. What do you think are the most important things? The synthetic data or something else?
Yeah, that's a good question. So first of all, I think at that time the scores were all pretty weak on DocVQA for all the models. So we could obtain 74, and I think the state of the art was not much higher. I think, yeah, how you can improve the score is, yeah, with several things. So first of all, the thing we mentioned about the number of tokens per image, we saw that this is clearly a bottleneck, and with even with 320 tokens per image, it's still I mean, it's still not that much. You have models like intern VL 4K, things like this that has uh, more than 1,000 visual tokens per image. Same for the models like Lava. So even 320 tokens per image is still some very reasonable number. And second is because he wasn't trained on large-scale synthetic data sets like dogmatics and so on. You can see probably here um, we didn't have that many document understanding data sets. It was mostly like, for example, render text, it was just text transcription. But for document understanding data sets, we had DocVQA that contains just 10,000 examples. And then for the other data sets, it was mostly, yeah, just pure OCR. Uh, so the reason is that, yeah, we didn't really have a lot of data sets to teach this ability. So I think it comes from these 2 points.
Thank you.
And actually, I have a question myself. So, as you know, I believe you guys curated obliques, so on also other great pre-training. datasets, for fine-tuning a LLM towards a multimodal LLM. And I believe, you guys also fine-tune easily through LoRa or directly, the LLM weights when you do this like more like a second stage pre-training outside the LLM. And are there any concern, or is it possible that, because this training distribution will be very different from the original LLM training distribution, so that, this additional gigantic training stage would, influence the original LLM capability or anything?
So, well, you mean that because with datasets like Obelix, for example, I think the distribution shift is less important than by training with image text pairs, because you
Yeah.
still have you still have very long documents, but you have in addition the images. And I think this is one of the reasons why it performed better for us during the pre-training by incorporating these long documents. If I go back to the previous ablation here, with the training on Lion only, so only on image text pairs, we saw that at some point we had a drop in performance, and it was because we were bad at few shot examples because the model couldn't really handle long text, simply because the image text pairs are very short. So by training, on Obelix, we kept a bit more the distribution of the text-only language model, and it performed better. But I don't know if it answers your question or if I missed something.
So I think it really answers my question. Thank you.
I actually have a follow-up question to your last, if I may, Peter.
Yeah, of course. Go ahead.
To your in the last slide, you mentioned for Idefix3, basically the main modification is to reduce the bottleneck of a too aggressive pooling. Could you elaborate on that? That doesn't mean that you're moving away from perceiver. Does it mean that, or are you just expanding the number of tokens and increasing resolution?
Yeah, that's a good question. So we didn't have time to do proper ablations for everything, but the idea is that while Idefix2 was focused on efficiency during the training at inference and training, we wanted Idefix3 to be less efficient, but potentially better at OCR. So what we did is that we simply use the pixel shuffle strategy to reduce the number of tokens. So it actually divided the number of visual tokens by 4. However, this is you end up with still much more tokens than you will end up with the perceiver resampler and with 64 tokens. So I don't remember exactly with Idefix3, but we had much more tokens per image, and this is also why we had a higher score on WQA. Yeah.
Do you think that going forward, things like perceiver, things like what they've done in Flamingo and in kind of early older models, these are going to disappear gradually, and what we'll end up with is basically just one big, very long stream of tokens and very big contexts?
So I think it really depends on first uh, if the models are going to be super good at long context, first of all, and also it depends on your application. For example, let's say that you want to extend VLM to videos, then to handle many frames and each frame with a lot of visual tokens, it's going to be super hard. So I think, especially for applications like videos, you will need a pooling strategy. Otherwise, it's just not very reasonable. Um, and then, I guess it really depends on your use case. If you don't mind having a bit worse performance on OCR, but then you can have a 2x boost at inference. it just makes sense to implement an efficient pooling strategy. So I think in the future, maybe we'll have different architectures with slight modifications like this, depending on the use cases.
Oh, thank you. And how can people try Idefics2?
So everything is online under the Hugging Face M4 organization on Hugging Face. Yeah, you can just search for the models on Hugging Face. You will find them.
We have a question from Julian Darley, who says, at the moment, it says there's a JSON error on the Hugging Face space.
Yeah, maybe which space? If it's the Idefics2 space, yeah, it's not maintained anymore, but the models should work. Maybe the space demo is not working, but
Okay, so people can just download the model weights and get
yeah, yeah. Also, all the datasets are available, yeah, under the same organization, so you can find a lot of stuff there.
I wonder, like, you know, you're operating under quite severe constraints here because you're trying to make a model that works across very diverse benchmarks, very diverse different tasks. What would you do if you really just wanted to focus on the task of OCR and doc VQA type stuff? What kind of compromises would you make? And, like, you know, is this really just about having a vision encoder that's really high resolution and that's the end of it, really? You know, what would you do?
Yeah, first of all, this. Also focus like do a special fine-tuning with by oversampling the datasets on OCR and on document understanding and reducing a bit, for example, the proportion of datasets around math or things like this. Yeah, I think it's just a question about your fine-tuning mix, how like which proportion you want to attribute to each category. Like for example, here, of course, if you want to be good at yeah all of these tasks, you need to have a balanced distribution. But then you can make it as you wish.
So not really architectural choices then, but really more about the data sets which are being used to.
Yeah. First of all, you need to reduce the bottleneck of the pooling strategy, and then yeah, it's just about data.
Okay, thanks. Peter, did you have any more?
But then I believe we also don't have much more questions from the audience.
Cool. Well, we're pretty much at time. Thanks so much. Thanks, Hugo. That was a really fascinating talk, really interesting work. Thanks so much for that. Thanks, Peter, for running the QA. Thanks again to George. Thanks to the sponsors, Evolution AI. See you all again next time. Bye.
Thanks.